This is AP Calculus BC, and in this video, I'm going to talk about section 10.3, tangent lines, arc length, and area for polar curves. We really talked about tangent lines with polar curves in section 10.2, so I'm not really going to focus too much on that. You can go back and reference those notes if you want to look at tangent lines. But for arc length and area, these are things that are going to be slightly different in the polar form than they were in our rectangular form, in our, the parametric representation of our rectangular form. When we talk about area in polar coordinates, we have to take into account how we measure the coordinates in the polar coordinate system. So when we vary our theta value, we're essentially going counterclockwise around the pole. So when we find an area in a polar coordinate system, using the idea of the theta value varying, and then obviously the r value being the distance out from the pole, then what we start to create are essentially sectors of area. And so you can see here, as this polar curve, r equals f of theta is rotated or created by rotating around the pole, that area that is then created inside of that polar curve is measured from the polar curve back to the pole. And so any of those regions that I have, if I break it into subregions, is essentially going to be a sector of a circle if I made the region small enough. So when we find the area of a sector of a circle, well, it's just the area of the circle times the percentage of the circle. So pi r squared times whatever the theta value is over 2 pi, that would give me my percentage of the circle, and we end up with 1/2 r squared theta. Well, that would be if our theta was a large value. In our case, we're breaking this into a bunch of really tiny subintervals, and these sectors are going to have a theta value then of d theta. It's kind of like when we were looking at rectangular approximation, we would have a dx as the width of the base of our rectangle. Well, now for us, the d theta sort of replaces that when we're in a polar form. So you can see each one of those sectors of area has a value of 1/2 r squared d theta. And then when I find that actual area, I'm just going to sum up all of those little subregions of area to combine them together. And that's where this formula for the area of a polar region comes from. So it's sort of a variation of what we did with rectangular approximation now in polar form. So let's take a look at how this would be used. So this one, we've got this curve that is a 4-leafed rose, and they want us to find the area enclosed by one loop or one petal of the 4-leafed rose. Okay, so in terms of setting these up, it's essentially a formula that you're going to use. So you can see in this case that that loop is bounded by negative pi over 4 and pi over 4. So I know I'm going to do the integral from negative pi over 4 to pi over 4, and it's 1/2 r squared d theta. Well, my r in this case is cosine 2 theta, and then my d theta, and then I'm just going to plug that into the calculator and get my solution. It turns out for this one that it's exactly pi over 8, and that's pretty simple to do. Now, the hard part on these in a lot of cases is going to be finding the limits of integration. In this case, it was very clearly shown in this diagram, right? These are the limits of integration. But sometimes we're going to have to take our equation, we're going to have to set it equal to 0, and then we're going to have to find some consecutive theta values that will then constrain one of those pieces of a curve or whatever part of the curve we're trying to work with. Okay, so on this next page, what I have is an exploration that just helps explain where the 1/2 r squared d theta comes from. So I'm not going to go through this, but it's an example that you can use. If you want a little further clarification on the 1/2 r squared d theta, you can work through this exploration, and it'll sort of walk you through step by step where that comes from. You can also read through that idea in your book if you want to see a little bit more. Okay, so another application of calculus with polar curves that we're going to look at is the idea of arc length again. So when we measure arc length, remember before we were kind of thinking about Pythagorean theorem, we would do like our dx squared plus dy squared, take the square root of that to find the length of that line segment. We're still thinking of this in the same way, but the difference now is we don't have an x and we don't have a y. So what we're going to do here is we're going to measure this small piece of our arc length is going to be treated like a line segment again. But now you can kind of think of this as a right triangle, but the sides of this right triangle are no longer dx and dy. What I have here is dr, which kind of makes sense because you can see I have the two different r values that are sort of defining the edges of this sector, and one of the r values is larger than the other. So dr would be one side, but the trickier part is this r d theta piece of it, because we have to use a little bit of geometry with this triangle to find the length of that side. So that side is r d theta, and then the other side is dr. Well, using that same general premise then, all I'm going to do is I'm going to go through and I'm going to set up the length of each one of those small pieces of my arc length, which is essentially a line segment. It would be the square root of the sum of the side lengths squared for that right triangle. And then we just do a little bit of algebraic manipulation here to get this into the correct form. And the way the algebraic manipulation works is just by multiplying by something convenient to make this simplify down. So what we do is we multiply by d theta over d theta. And when you do that, you're essentially going to leave the d theta that's in the numerator outside of the square root. But if you move the d theta that's in the denominator inside that square root, both of those terms get multiplied by 1 over d theta squared. And then you can simplify down and you get this representation of the arc length with polar coordinates. So this is something you're probably going to want to memorize. You could go through and derive it. The hard part is you're going to have a hard time remembering or figuring out where that r d theta comes from if you're trying to do that quickly on your own. So that's probably something you're going to want to memorize. Okay, so let's take a look at an example of using this. So this says find the length of the limacon r is equal to 1 plus 3 sine theta. Okay, so we want to find the length all the way around this. So we essentially want to create or complete one cycle of this curve. So what I'm going to need to know if I'm going to set this up using this formula is I need to know dr d theta. So dr d theta in this case is the derivative of the r equation with respect to theta. You can see it'd be 3 cosine theta. And now just from that, that's really all I need to know. If I want to find the length, one cycle of these curves is typically going to be 0 to 2 pi. We'll talk about this a little bit more in a minute. This one, it's 0 to 2 pi. And then I'm going to do the square root of my r squared plus dr d theta squared. So my r was 1 plus 3 sine theta. I'm going to square that. My dr d theta was 3 cosine theta. I'm going to square that and then multiply by d theta. Now, this is just going to be calculator work again. You need to know how to set it up, but then at that point, you're just going to plug it into the calculator. So for this one, you would get a length of about 19.377. There are going to be certain situations where these will work out really nicely and you can solve them out by hand, but for the most part, I'm not going to ask you to get stuck in kind of an endless work, cycle of trying to solve through using trig identities and going through all the algebra that you have to do to get these solved out. A lot of times it involves trig substitution. I don't want you to mess around with all of that because you lose focus on the big picture, which really what we're trying to focus on here is arc length. So just do the setup and then plug it into the calculator. Okay, so now let's look at just some kind of general examples and talk a little bit about how some of these work. Okay, so this says for r is 3 sine 2 theta, find the area of one leaf and the length of one leaf. So what you might want to do in a situation like this is you might want to graph this. So 3 sine 2 theta, let's take a look at that graph. Okay, so here's my calculator with the 3 sine 2 theta plugged in. For my window, I went from 0 to 2 pi because that's what it takes to complete one cycle of this graph. And when I plot that, you can see I get this 4-leafed rows here. So what they want us to do is they want us to find the area of one of these pieces, and they also want us to find the length of one of these pieces. So the tricky part on this is that we really have to know what our limits of integration are. So sometimes you can do this on the calculator. Like for example, here I can trace When theta is equal to 0, you can see I'm at the pole. If I trace to theta is equal to pi over 2, I'm at the pole again. So that's actually going to be one leaf. But what you could also do is you can use a little bit of trig and solve a trig equation and solve it out. So what I meant by using a little bit of trigonometry to solve it out would be find the values where r is equal to 0. I could set 3 sine 2 theta equal to 0, and I'd get sine 2 theta equals 0. Then I can make sine 2 theta cosine theta sine theta, or 2 sine theta cosine theta, and then I would get 0 and pi over 2 as two consecutive values there. So that's kind of how you can set that up. If you're not really sure, you can actually go through and solve it out. But from the standpoint of now finding the area and finding the length, well, now we know what our limits of integration are. So for the area, I'm just going to go from 0 to pi over 2. And I know I'm going to use 1/2 r squared d theta. So 1/2, my r was 3 sine 2 theta. I'm going to square that, multiply by d theta, and then I can just plug that into the calculator. When I plug this into the calculator, this actually has an exact solution of 9 pi over 8. When you plug it in that way, you're just going to get the decimal approximation for that, which would look like about 3.534. But what you can also do, if you want to check for an exact solution, a lot of times if you take the decimal answer that the calculator gives you and divide by pi, sometimes you'll be able to identify what the exact solution is when it's an answer that's in terms of pi. All right, so the other thing they asked us to do here was to find the length. Well, for the length, I know I'm going to integrate from 0 to pi over 2 again. And remember, we need to know what our r squared is, and we need to know dr d theta. So I'm going to do the square root of my r squared, which would be 3 sine 2 theta. That would be squared. And then my dr d theta, in this case, would be 6 cosine 2 theta. So then I'm going to square that and then multiply by d theta. And again, we would just plug this into the calculator. In this case, finding the exact solution, it's hard to identify from the calculator. So you could just write it as a decimal of about 7.266. On some of the homework questions, they might ask you for exact solutions. Don't worry about that. All I'm asking you to do is get the decimal answers, because I don't want you spending a bunch of time trying to solve out these integrals that can be very, very time consuming when you start getting into all of the trig identities and all of the trig substitution that often shows up. I don't want you to do that. So just plug it into the calculator, get the decimal. Even if the Wiley Plus assignment counts it wrong, that's okay. I just want you to work through these, get the setup correct, work through them. You can check your answer versus what Wiley Plus gives you. Take their exact answer, turn it into a decimal, and make sure it matches up with yours. Okay, so last thing here that I just wanted to, I don't want to go through this entire exploration, but I want to go through one last thing. There are going to be some situations where you're going to want to find the area between two polar curves. And I just want to show you the setup for this, because it's pretty intuitive for the most part, but the thing that you have to be very careful about are intersection points. So this one, what they're wanting us to do is they're wanting us to find the region in quadrant 1 outside the circle R1 is equal to 4, and inside one leaf of the 4-leaf rows 6 sine 2 theta. So the region that we're trying to find the area of is actually this region in here, right? And so when you think of this from the perspective of, okay, how do we do this with the areas? For the areas, we were taking really small sectors. And if you think of how my sectors are set up here, if I got the area of everything inside that blue sector, that would be the area inside that petal of the 4-leaf rose, or with the leaf of the 4-leaf rose. But then I would want to subtract out or take away all of this part inside the circle, right? That sector of the circle needs to come out of that. So essentially what I'm going to do is do a difference of the two area calculations, and we can combine that into a single integral. So what we would do in this case is we would take an integral. We know we're going to have our 1/2 r squared d theta, but our outside radius, if you want to think of that as the the larger piece, the overall area of the entire sector would be the 6 sine 2 theta. We would square that. If I just integrated that with respect to theta, that would give me the area of the entire leaf. But then what I want to do is I want to subtract out the area of that piece of the circle that's inside that leaf. And so what I have to subtract out there is that r is equal to 4 being squared. So essentially what I have here, when you look at the distribution, I have a 1/2 r squared d theta minus a 1/2 r squared d theta. So that's all I'm really doing. Now, the limits of integration here, I would have to find the intersection of these two curves. So I'm just going to call this, let's just say theta 1 and theta 2. And the way I would find those intersection points is I would just say, okay, when is 4 equal to 6 sine 2 theta? And then find the theta values, and then you can integrate. So it's not that difficult to do. There are a few situations where you might run into one issue, which is every once in a while, these things that appear to be intersection points are not true intersection points, right? They're what we call collision points, when they're at the same point for the same theta value, or the same r value for the same theta value. Sometimes you're going to get differing theta values. And if that were the case, then I would have to integrate the part of the curve that's the petal over its theta values, and then the part, in this case, that's the circle, over its individual theta values, and then subtract those areas. Instead of having a single integral, I would just have two separate integrals. But most of the time, you can just go through this process. You can set the two curves equal to each other, and that'll give you those intersection points. Okay, so a couple things that are in this packet that I wanted to show you. So I mentioned in the 10.2 lesson that you don't need to know the names of these curves, and you don't necessarily need to know the standard forms of these curves. But one thing you do need to know is that in order to complete one cycle of these curves, it's not always going to be 2 pi radians. So for example, when I have r is equal to a constant, you can see it takes 2 pi radians to make one revolution of that circle. But if I have r as a sine theta, it takes pi radians, or r as a cosine theta, it takes pi radians. So you're typically going to have a calculator that you can use to verify how long it takes to make one cycle. And what you can do is just graph it and watch the graph being created on whatever theta values you choose. If you choose for the graph to go from 0 to 2 pi, and you see that that circle is being traversed twice in the 2 pi radians, then you know that your limits of integration, or the values that you would use, would go from 0 to pi. So keep that in mind. It's not always going to be 0 to 2 pi. So here with the rose curves, kind of the same thing. You can see when we have an odd n value here in front of the theta, it takes pi radians. When we have an even n value, it takes 2 pi radians. So again, it's not so much that you have to memorize that. It's just that you have to know that it's not always pi radians. Same thing with the cosine rose curves. Sometimes we're going to have pi, sometimes we're going to have 2 pi radians. And also with these limacons or limacons, same idea. We're not always going to use pi or 2 pi radians every single time. There's going to be certain situations where things are going to change. And I don't want you to try to memorize all of these special scenarios. I just want you to have it clear in your mind that we're not always going to assume 0 to 2 pi. Okay, so last thing, at the back of this, I did include a worksheet. This is not for you to turn in. You have an assignment in Wiley Plus, which is your assignment on 10.3, but this is just extra practice. So this will be something that will be good to use to review for your test, or if you want some extra practice after you've finished your Wiley Plus assignment.